So hello everyone, this is yet another video on the AI-171 crash and on the fuel control switch system. Now, since the last video I posted in December 2025 on the GM ignition switch and this switch, the deadly parallel between them, I looked into the operation of the FC switches during the engine startup phase on the ground as the aircrafts are being pushed back. Of course, not from the AI-171 but from other aircraft, the same class, the B7878 Dreamliners. I did it because I suspected that there is a possibility for the engine excitation to reach this system, fuel control system, the switches system, if the frequencies were to clash. Now I am led to believe from what I'm going to show you here in this video that safety seems to be on the edge when it comes to the fuel control switches. That's plainly because I'm finding a serious crossing of the engine excitation with the operating spectra of the fuel control switches. It's not necessarily a reason to be panicking about, because aircraft are flying, of course, with the same characteristics more or less of the engine excitation and the operating spectra. I'll try to explain why we might have seen something different happen in the AI-171's case. Okay, so let's get started. This is what exactly I've done. I got hold of 3 cockpit videos of the engine start phase from real-world B787 flights. Thanks to the YouTube videos being posted by justplanes.com, a big shout out to them. And from these audio samples, I of course extracted the spectrograms in those intervals in which only the FC switch operations were taking place. I had to obviously weed out things like cockpit conversations between crew, ATC and crew, and ground and crew, and all and other operations other than the FC switches. Now, also needed, I went for a 4th flight independent of these 3 flights in order to capture the engine's content from the takeoff run. Because if you remember the preliminary report of the investigators last year, which it clearly said that once the AI-171 got airborne, reached a speed of 180 knots, both the fuel control switches transitioned from run to cutoff within a 1-second interval. So I am trying to see if I can reach that same condition out here from other data, the public domain data, of course. And well, I may not be able to prove that yes, that indeed was this or this indeed was the cause of the transition here, but at least I believe I have narrowed down the possibilities, or at least opened up a new room, something for thought. So the $1 billion question, who is the likely culprit in the run cutoff transition? Well, I cannot, as I said, prove it, but I can at least get a little nearer to it than how far I've gone till now. All right, let's get to the first video now. The cockpit video. This is a video of a flight between New York, JFK, and a place called Casablanca. And I'm calling it SNYCB for short. And on top left, you see a timer 00.00 and so on. That is the timer which is going to also start ticking once the video plays. That units are in milliseconds, seconds, minutes, and hours. Of course, you need to just focus on the milliseconds and seconds, because the operations here that you are seeing 15.363 to 55 and 21.58 to 75, they are all of course in just milliseconds, but please don't mistake this for the actual duration of operation of each switch. It is not. These are only the durations in which the acoustic content was very strong. There's always a silent part of the operation which doesn't produce any content out there. So the actual time duration of an operation of a switch is not merely this time, but much beyond this too. So because there was, and there probably still is, some body of thinking that the pilots themselves did the transition and within that 1-second interval. So this should not mislead you into believing that that might have happened here because of these timings. All right, so just focus on the timer there and these 2 intervals out here. They're going to be always present during the video, and try to see if you can sync the 2 things together as they happen. All right, so let's get started.
Roger, clear to start engines.
Okay, start up sequence 2 and 1 simultaneously.
Roger, 2 and 1.
Start right engine.
Right.
Run. Start left engine.
Left.
Run.
All right, so I guess you could clearly see the switch being operated. In fact, this is one of the only videos that which clearly shows the camera focusing on the switch itself. So you have an additional information, visual information too, apart from the audible one which you hear the switch operation. Anyway, let's get to the spectrogram. So this is the spectrogram of the right switch operation between 15.363 and 15.55 seconds. So you see kind of comb-like structure roughly there. And I've thrown in a line of at 660 hertz there. I'll come back later to what this line means, and you will also see why it's very important. For the time being, just pay note to the fact that this 660 hertz is running through a very strong part of the FC switch operation spectrum. Now for the left switch, yes, this is a little clearer than the previous one. It's also got a clear comb-like structure. Again, 660 hertz runs to the strong part of it. Now let's get to the second video. This is for a flight between Heathrow, London and Amman, Jordan. It's a Royal Jordanian Airlines. So you know what to be looking at, just like the last video. Okay, let's get going.
Start and push. Please make sure the area is clear. All the doors and panels are closed. When you're ready, advise me to release parking brake.
Yes, I already said that. Everything's all complete downstairs. Release brakes, please.
Parking brake is released.
Ground and fly, they can clear the site of your engines.
Okay, starting right and left. Okay, all parameters are good. Starting right and left. Auto start.
Right, so you can see the two engines have started. If you look at the auto start on the cockpit display there, 137 and 125 RPM there. Let's get to the spectrogram. So here's the right switch operation. 35.8 to 35.92. Again, a similar comb-like structure that you saw in the previous flight of the New York Casablanca NYCB. 660 hertz, yes, like always, it is still cutting through the strong part of the spectrum. For the left switch operation, that is the place where it occurs, 36.98 to 37.05. Same thing holds here, 660 hertz, cutting through a very strong part of the spectrum. Now let's get to the third video, the last in the 3-video series here on the cockpit engine startup phase. So this is between Stockholm and Los Angeles, STLA, as I call it. Yeah.
Okay, on gate 34, I guess.
Yeah, most likely.
Okay. Sure, brakes are released. Commence the pushback.
Brakes are released.
You can start 2 and 1 in sequence.
Copy that. We'll start 2 and 1 in sequence. Oliver, start right engine. And start left engine.
So I guess you could clearly hear the right switch click, but the left was a little bit lost in that ambient noise out there in the hiss. So the spectrograms that you're going to see also reflect that kind of very clear character and little less clear character. So let's get this first spectrogram, the right switch. So this is the one 21.61 to 21.87 seconds. That strong content you see to the left of this comb structure at around just past 21.5 seconds, that's the engine selector switch, which is on the roof of the cockpit there. So once that's set to run, it's the engine is selected there. There are two selectors, of course, one for the right and for the left. Anyway, the 660 hertz is still cutting through the strong part of the spectrum, which is all that you need to take note of here. And when it comes to the left switch, as you saw, it was quite muffled there to hear, and no surprise that the spectrogram is also a little bit of less clear than the right switch spectrogram. But yes, the 660 hertz is still cutting through the strong part of it anyway. Now let's get to the takeoff run. The takeoff run, the timer is in the top center out there, and this is between Amsterdam and St. Martin. Also, of course, a Boeing 787 Dreamliner. That's very important because I need to ensure that the character of the engines are no different from that of the A171. The things you need to watch out for here are the V1 call automatically coming from the cockpit and the rotate that comes from the crew member. Okay, let's get going.
Thrust is set. 90 knots. Shift.
5, domain 230 degrees, 12 knots. Wide left, Echo 5, clear for take. Echo 5, wide left, clear for take, tailor 105.
E1. Rotate. Positive rate. You're on.
Right, so I guess you must have surely noticed that shudder in the cockpit somewhere around 47.5 to 48 seconds. And of course, I guess you could clearly match the V1 at 39.25 seconds in the rotate call from the crew member. Anyway, let's get to the spectrogram. 39.25 is the V1 and 40.5 to 41.25 is the rotate. So that's the V1 there, 39.25 seconds, and that's the rotate out there. And if you look at the bottom of the spectrogram, and if you go back to the video, you would have heard a lot of duck, 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 duck sound as the aircraft was really reaching the VR speed. The bottom of the spectrogram, around 125 hertz, is that discrete part of field-like structure. No? That's exactly all that content flowing into the microphone here. And you see that just past this line 43.25 seconds, that significantly drops. So that's because the nose wheel is now off the ground, and no longer do you have any ground input coming of that strong kind. But yes, you do see that content still persisting, a little more weakened content, but that's, I guess it's because the nose wheel is still spinning, so it's not lost all the content there. And something from there is still reaching the cockpit. Anyway, the point to note is not none of these things, but really the 660 hertz line is here. And you do see a strong content at 660 hertz that seems to possibly even get stronger as you're nearing the VR. Well, this rings a bell, obviously, right? Because if a frequency seems to be from an engine seems to be the same as that in the FC spectra operation spectrum, so it's likely it's a door that's open in the FC switch system to invite this energy at this frequency into the system. Well, does it really mean a resonance and immediately a transition? No, it does not, because obviously all these flights, which videos, they are all flights that flew and they're probably still flying today. So exactly what might have been the reason, I'm trying to offer the best explanation I can, because I'm working with very limited data, as you obviously can see. I can only make engineering guesses or engineering judgment. I can't prove anything or establish anything. Anyway, there's a little bit of zoom in of the same spectrogram out here, in case you couldn't figure out things very clearly there. You can see the up to 250 hertz, you see a strong content lying there to the left of 40.25 seconds. That's coming on the ground and weakens as the nose wheel gets off. And of those at the 660 hertz there, you see component being relatively strong there. All right, so now let's summarize all the observations out here first before we get to any analysis. So what we have seen is that there's a kind of comb-like spectral character of the FC switch operation from 500 to 2000 hertz, and also the same range in which all the engine orders are also going to be there. They're all lying in the same 500 to 2000 hertz. If you go back to my very first video, which I posted before the preliminary report came, you would have seen that many of the frequencies there, which I could capture from that teenagers video and all the spectrogram analysis, you do see them lying in this 500 to 2000 hertz range. And also we can see that just on the nose wheel getting off the ground, there's a spike in the 660 hertz the amplitude there at 660 hertz. Right, so now let's see what happens when you try to argue on the clashing of 660 hertz from the engine with the content in this FC switch operation. So I'll start with the topmost picture of a GEnx engine to get to the my point here. So the GEnx is the one that powers all the Dreamliners. And if I were to represent the energy output of this engine, I might picture it like this, with all the green part being, of course, obviously the useful one, the thrust, the electric power, and the actuations. And there's always, of course, a red part in anything, any system, in mechanical system. There's nothing that's 100% efficient, so it's not fully green. So that's the waste part. But this is not a waste in the sense of being a commercial loss. It's a waste in an engineering sense. It's a waste of what? It's a waste of energy. And you can't just wish away energy and say, get lost, I don't need you. Sorry. Energy cannot be asked to leave where you want it and as you want it. It will flow in its natural way through the system, and it will do work. The only way energy can can be used up is by doing work, either as dissipation itself, in which case you can't. It's a non-conservative system, or maybe by excitation of something which is possibly conservative. Anyway, okay. So where all does this waste go? It does go to the structure, and that's exactly why you saw the cockpit shudder at between 47.5 48 seconds in the last video that you saw. It does get into the cabin too, of course, as you very much, I think, will recognize, because you are given earplugs in long haul flights to cut off the hum from the engines. But these are just annoyances at the most. The real danger is because, at least in the A171's case, on possibly a potential danger in all other aircraft too, is that part of the waste getting into the cockpit. Now let's see what it means from a structural dynamics point of view. So before I get there, I need to first look at the forward fuselage structure and the nose, which Boeing calls a section 41, the flight deck structure. I look at this, whatever is inside this, because this is a structure that's on which you are having the IMA chassis, the Integrated Modular Avionics chassis. Again, this is manufactured by one of the partners of Boeing. And on this chassis, the entire cluster of cockpit instruments, the displays, the dials, knobs, levers, everything on that. All right. Now in the IMA chassis, there's something called a thrust control module, the TC module as I call it for short. And as if you look at a TC module there, you can clearly recognize what I'm after. It's the fuel control switch system, the FC switch module. And of course, in this FC switch module are the two FC switches themselves. Now, well, I didn't put up this just to look at the architecture of things out there. I put up this because I wanted to bring out the concept of sources and receivers here. So what do I mean exactly by that? Now, if section 41 flight deck structure is the source of engine's energy, the IMA chassis is going to be the receiver of it, one of the receivers. Now, again, in turn, the IMA chassis is a source too for the TC module, so that becomes the receiver. And in turn, the TC module is a source for the FC switch module, which becomes the receiver. And in turn, yes, the FC switch module is a source for the FC switches too, but I'm not extending to that, which you can obviously see. It's quite, you can extend it on your own. So if you are given sources and receivers, let's see what happens when a source and receiver's frequency clash. So let's say we've got a receiver with 3 spectral lines, F1, F2, F3 frequencies, and the source is clashing here with the same frequencies, F1, F2, F3. So if we were just a simple physics single degree system, obviously this means straightaway resonance, nothing else. But we are talking of complex shaped modules like the TC module, FC switch module, and IMA chassis, which have a lot of modes in them. So the picture is pretty different from a single degree system. So let's see what matters as far as the multi-degree system is concerned, like any of these modules that I just looked at there. So the two things that matter here are the transmissibility as a function of F, the excitation frequency, and the participation factor, gamma J. The J here in both cases refers to the jth mode of this multi-DOF system. The multi-DOF system, of course, is any of those systems like the TC module or the FC switch module. All right. So now, what exactly is participation factor? Well, analytically, you can show that the participation factor looks like this. When you create an analytical model and do something called a normal mode transformation of a multi-DOF system, you would end up seeing something like this. I'm not going to go too much into theory, but I just want to put a few things essential to the talking here, and I'll try to give a simple everyday analog of the participation factor. Anyway, on the right side, what you see a CJ bar transpose and F naught, the two key things on which participation depends. The F naught is, of course, a source excitation vector, which is all forces coming, forces and moments, anything in the vector. And the CJ, the transpose is, of course, only for conformability of multiplication, and the bar there is the result of normalization by what's called an M norm. All right. In the denominator, you see that that's just a Euclidean norm of the F naught vector. So gamma J is really non-dimensional quantity. See, a very everyday analog of gamma J is like, imagine that you've got a speaker speaking English to about 6 people in front of him. The 6 people are an American, an Englishman, a Japanese, an Italian, a Chinese, and a Russian. So not all of them understand English equally well. Probably some of them never understand it too. So the American Englishmen, surely I guess they understand English. So if you would expect them to fully absorb whatever the speaker is saying. So which means their participation factor is pretty high, almost equal to 100%. To the extent that the others can understand English, they have some participation too. Of course, a person who can understand nothing of English, he is probably having a null vector in the CJ. So you would find a participation of 0, 0. So a participation factor kind of measures the extent to which a receiver absorbs input from the source. The input being F0, in which case it was the speaker, and the CJs were the respective extents to which the listeners were receiving it. Okay, anyway, let's get going. What I want to put up here is a kind of map, again a qualitative map, just based on simple common sense, engineering common sense. So you can see that transmissibility is dangerous when it's high, and participation also is dangerous when it's high in a mechanical system. So this map should look like this. The high zone being obviously in the red and the low zone being the green. So if you take those 3 flights, which cockpit videos of 3 flights, the New York CB, the NYCB, and the STLA, Stockholm, Los Angeles, and Heathrow, London, and Amman, Jordan thing. Yeah, and of course also the last video of the Saint Martin, the Amsterdam Saint Martin flight. They all are surely in the green zone because nothing happened to those flights. But well, that obviously means that something must have happened here in the A170's case. But as I said, it's impossible for me to really know which of these dots is the one that pertains to the A171. But I'm guessing it's something like somewhere in that red zone, somewhere in that red zone. And this also, I think, going to be hard for the investigating agency too, because I'm told that about 200 parameters are logged into the aircraft at any point of time. But I kind of believe that those 200 parameters might not include things like sensing the responses of these modules. In order to really resolve these kind of issues, whether the transmissibilities are high or the participations are high and such things, because they are more of interest to structural dynamics people, not to interest to pilots. So I'm sure that will also make it harder for the investigating agency, unless, of course, they find with other data that they have got only with them, that they can reach a more, make a more conclusive statement on what exactly happened there. Anyway, so now let's say we have a 660 hertz frequency, and we are looking at what happens when something is really functioning both as a receiver and in turn as a source. So as a receiver, there are 2 things obviously that matter when you have a 660 hertz input to it. So one is the participations of various modes, the other is the transmissibilities of various modes. Transmissibility again is something only that's a scalar characteristic, solely dependent on the proximity of the excitation frequency at 660 hertz to the motor frequencies that are sitting there. Alright, so let's look at a scenario where we have 2 modules out here, the TC module, which is both a receiver from the IMA chassis and a source to the FC switches module. So as a receiver, what do you expect from the TC module? So its own response as far as the bounce component is concerned. We remember that in one of the videos earlier I had mentioned about the bounce mode being the one that's obviously should have been there in order for the transition to have happened, because the bounce mode is behind it. Bounce mode, excitation, strong excitation in the bounce mode or a strong response to the bounce mode would obviously bring the switch out of its socket, and in the environment that it is sitting in, there's surely some amount of a lateral component across the bounce mode, and that's enough to make the transition. So everything boils down to the extent to which the response bounce component is getting affected by all the participations and transmissibilities of the modules out there. Now in turn, if this, as this TC module is also a source for the FC switches module, what's going to happen is it's going to obviously provide an excitation to the FC switches module, and that excitation is to the extent the response is limited by all the participations and transmissibilities. So it's a response bound excitation that's acting on the FC switches module. And in turn, FC switches module is now a receiver, so its own response does depend on its own participations and transmissibilities too. And therefore, whatever it throws into the switches themselves would be again this response bound excitation. Right. So now let's try to get to the final question, and try to see if we can find some answer to this. So at 660 hertz, we have seen that in order for transition to happen, there should have been a force, F bow as I call it. It's a force required to pull the switch out of its socket. But this force is not coming from the pilots, it's coming from the environment in which the aircraft is flying, that is AA-171 is flying. And that F bow is a lot more than the typical force that a pilot applies in order to do the transition cutoff to run during the startup phase. So who is the likely culprit? So there are three candidates as I see it. One is the FC switch itself. The next is the FC switch's module. The third is, of course, the TC module. Yeah, it's also possible, of course, that it's a combination of both the FC switches module and TC module might have frequencies that might, as coupled frequencies, might clash with the 660 hertz. I can't rule that out because as I said, I'm just someone working public domain data just from YouTube, and I don't expect I could go that far to really figure out the numbers from all these which are needed really to answer these questions. Anyway, as a person in structural dynamics, I would look at it like this. The FC switch itself I consider as a very unlikely candidate for the 660 hertz clash there. Why I'm saying that is because 660 hertz is a pretty large frequency. So if you really expect that the switch itself has got that frequency, my gut feeling with various systems that I've been working on is that you would need a very massive force to pull this switch out of its socket, which the pilots certainly don't use. So that kind of makes it very unlikely to be the candidate as the culprit. So that brings us to the next possibility of the FC switches module being the culprit. Well, I place this on as a moderately possible culprit because though I obviously don't have any numbers to justify it, I mean between the FC switch and this module, I would place more suspicion on the module because there are a lot more modes here and therefore a lot more possibility from a statistical point of view, no more than that. But if you come to the TC module, I somehow have a high suspicion here on this one being the culprit behind the 660 hertz frequency, rather the absorbing the 660 hertz frequency, content is 660 hertz. Now why I'm making that statement is because what happens whenever flights land. So there's a lot of impact that's happening on land. It's not necessarily that the landing has to be very hard or something like that. Even a soft landing does have a kind of shock that passes on to these modules. So the TC module is the heaviest of all these three, therefore the largest inertial forces that you would expect from the impact are going to be seen in this TC module for the same acceleration input. So over a period of time, my guess is there has been some degradation of frequency in the TC module of the A171, bringing it down maybe from something like about 1000 hertz or so, whatever it might be in the other flights that you saw, in a normally healthy kind of module system there, to down to 660 hertz on that fatal flight. Well, there is again, as I said, just a hypothesis. I can't prove it obviously because I don't have any clear data to be with me to prove it. So anyway, that's as far as I can take it. So yeah, this should at least be an eye-opener to Boeing and to people the stakeholders involved in the systems, the manufacturing and characterization and qualification. So I would say that this safety seems to be on the edge, if not being obviously a sure threat. It's at least certainly somewhere in the margin of safety is kind of questionable. And with several flights, if there are hard landings, I'm sure that is a red flag as far as these modules go, because there's a possibility of degradation of the frequency, which could happen and cause this resulting frequency to drop down to 660 hertz, and then anything like this possibility happening. Okay, thanks for listening anyway. Yeah, let's hope for the interim report coming out soon and something interesting. Thank you.